For this example, we want to show that f of x has a maximum and a minimum value on the interval, closed interval AB. And the extreme value theorem is going to guarantee both max and a minimum, global max and a minimum on that closed interval because the function is continuous. And so what we need to do is we need to check out any critical points that are in the interval and the endpoints of the interval and figure out which one's the biggest and the smallest. And so to get the critical points, we need to take the derivative. So derivatives of polynomials, we just take term by term. So we've got 4x cubed minus 6x. And we need to find the critical point, so we need to find out where is this 0 and undefined. And so to be able to get where it's 0, certainly we want it factored first. So we pull out the greatest common factor, which would be 2x, leaving us with not 4, how about 2x squared minus the 3. Okay, so when we have f prime equal to 0, we just set each factor equal to 0 and solve. So we've got the 2x equal to 0, divide both sides by 2, that gives us x equals 0. And the 2x squared minus 3 equal to 0, we would add over the 3, divide both sides by 2 to get x squared equals 3 halves. And then when we solve that, we have to take the square root of both sides, so we plus and minus the square root there of root 3 halves there. And so, I mean, I could go ahead and rationalize this and so forth, but I know that I'm just going to end up plugging this value back into the original function, and we might as well not mess with it because I'm going to either square it or raise it to the 4th power, so I'm just going to leave it alone. But what I do have to assess is which one of these are in our interval. And so 0 is in the interval. It actually happens to be an endpoint of the interval. But as far as the plus and minus, the square root of 3 halves, only the positive one is in the interval. So the negative one is not in the interval. And so we don't care what's happening. We're restricting our vision to the interval 0 to 2, and so any critical points outside of that are going to be irrelevant. Also, when we're dealing with critical points, we always need to make sure we assess where f prime could be undefined. But this is a polynomial, and so it's never undefined. And so we don't get any additional critical points there. So now that we have found our critical points, it's a matter of plugging in values. And so we need to plug in our critical points that are in the interval as well as the endpoints. So our critical points, when we evaluate, we are plugging in 0. That was the first critical point that we got. And the second one we got was the positive root here, positive root 3 halves. Okay, so when we plug in 0, that's 0 to the 4th minus 3 times 0 squared minus 2. So the first two terms are 0, leaving us with negative 2. And then for the next one, it's a more obnoxious number to plug in, but since we're raising them to even powers, actually the obnoxiousness is going to go away a bit. So we plug in the root 3 halves to our polynomial, and we see really the 4th power is squaring it and then squaring it again. So the first squaring it would undo the square root, and so then we square it again, leaving us with 9/4 there for the first term. And then for the next one, it's 3 times, and then the square root and square cancel each other out. And so we're looking at minus 3 times 3 halves, so that would be minus 9 halves. And then we have minus 2 that we need to evaluate. So, I mean, when you're computing these, we've got fractions, and so we're going to have to get a common denominator to be able to get the fractions added and subtracted. And so our common denominator is going to be 4. So I see that for the 9 halves, I have to multiply top and bottom by 2. So that's where the 18 on the top came from. And then for this minus 2, if I'm going to stick a 4 in the bottom, I'm going to have to multiply the top by 4 also, and so that's where the 8's coming into play. So we've got the 9 minus 18 would be negative 9, minus another 8 would be a negative 17 overall. So we're looking at negative 17 fourths. Okay, so that's our plugging in values for the critical points. Now we got to plug in the endpoints. And nicely enough, 0 is an endpoint. We already plugged it in, and we got negative 2. We already did this. It was already done. But then the new value that we do need to figure out what's happening at would be at 2, and so we need to plug in 2. So we'd have 2 to the 4th minus 3 times 2 squared minus 2. So 2 to the 4th would be, so that would be 2 times 2 would be 4, and there'd be 2 copies of that. So 4 times 4 would be 16. So we're looking at 16 minus 3 times 4. So 16 minus the 12, and then minus another 2. So that'd be like 16 minus 14, so that would give us 2 in the end. Okay, and so now that we have all of our plug-in values plugged in, we have to find the biggest and we have to find the smallest. And let's see, we've got 2, we've got negative 2, and we have negative 17 over 4. So we need to figure out what negative 17 over 4 is in comparison to negative 2. So we know that 4 times 4 would be 16. So this would be like negative 4 and then a little bit more negative than that. And so our smallest value is this negative 17 over 4. And our biggest value is the 2. And so we're able to make our conclusions now based on those values. And so we've got a global max of the biggest value, so that would be global max of 2 at x equals 2. And we would have a global min of the negative 17 over 4, and that would be at that positive root 3 halves. Okay. And I'm putting in the extra word there of global just to differentiate it from a local max or a min. And so, I mean, you could also just say the max on this interval and the min on this interval. Just having the word global in there drives home the point that this is the biggest and the smallest values that we can get on this interval.